Hello and welcome. In this video we want to take a look at the notion of circulation around a closed curve. Um, the concept of circulation is just, as I have written here, a specific instance of line integral along the curve. It is the integral of f dotted with t ds along the curve C, but now we're being very specific about what curves we're going to integrate over. And the curves that we're going to use are curves that start and end in the same place. They make a loop. They may make kind of crazy loops, but if they start and end in the same place, then we call it a closed curve. And so we'll be integrating over closed curves. So the circulation integral, which looks like this, we got this special fancy symbol for the integral now with a little circle in it. But it's still just an integral of f of t ds. Sorry, not f of t, but f dotted with t ds. And that little circle has no mathematical significance whatsoever. You are still doing an integral. You're still doing a line integral of a vector field along a curve. It just looks cool. It just looks cool. And really, I guess it's the writer of the integral's way of indicating to the reader that the curve that you're integrating over is a closed curve, that this is integrating around a loop. But there's no new math that you've got to learn to do this integral if you didn't already know how to do this integral. That is, if you did know how to do it, then you could do this. Okay. Let's do a couple of examples here. So the first example, I'm using this vector field minus y comma x because it is very circular. There's a lot of circulation, it looks like, right? Things are going around and around and around. And the curve that I'm going to use, the closed curve that I'm going to use, is a circle centered at the origin of radius r. I happen to have it drawn here at radius 2, but this calculation will be for any r. You can see little arrows indicating that it's going in the counterclockwise direction, which is, of course, the direction that the circular flow here seems to be going as well. So with my parameterization being capital R cos t, capital R sine t, then the r prime, so the derivative here would be minus r sine t comma r cos t. The circulation integral, which is just the vector, what is it? It's the line integral of a vector function along a curve, which can be written like that, or it can be written as p dx, the integral p dx plus q dy. So thinking of it this way, the p is the first component of the vector field, so minus y, and the dx is the first component of the derivative of, of r prime here. So we've got that, and then plus q dy, so the q is the x up here, and the dy is the second component of r prime, so r cos. Now I'm going to replace the y and the x here in terms of t's, and those are coming from the parameterization itself. So the y turns into an r sine t right there, and the x turns into an r cos t right there. So this becomes an r squared sine squared t plus r squared cos squared t. Aha, factor out the r squared, and the sine squared t plus cos squared t is 1. So this is just the integral of r squared, and r is just that constant radius. And so the integral of r squared from 0 to 2 pi is going to be 2 pi r squared, which is interesting. It's essentially twice the area of the thing involved. The idea here is that this is a positive thing. There is a lot of circulation, that the vector field is very much helping to move things along that curve. The book says something like the circulation is measuring the tendency of the vector field to flow in the same direction as the curve. So yeah. So let's take a look at this next example where the vector field is the vector field that's pointing exactly back to the origin. So at the point xy, you're looking at the vector minus x minus y. So no matter where you are, you're looking directly back at the origin. Again, the vector field is drawn when the vector is too short, otherwise you really can't see what's going on. Everything's been scaled down here. But the curve will be the same as the last example, where we're just going around a circle of radius r. And I think you can see that the vector field is essentially perpendicular to the curve everywhere. And I would expect that the circulation here would be 0, that there's no component of the vector field ever in the direction of the curve. So let's do that calculation. This is my parameterization, r cos t, r sine t for the curve. The derivative there, so r prime would be, what's that, minus r sine t, r cos t. That should be the same as the last example. Again, doing this circulation integral, so it's just the line integral of the vector field along the curve, but the curve is a closed curve, so we put the little circle there, and I'm going to do it as the p dx plus q dy. So the p in this case is minus x, the q is the minus y, the dx is, from the derivative here, the first component, r minus r sine t, and the dy is the r cos t, that goes there. Replacing the x and the y from the parameterization now, so x is r cos t, and the y here is r sine t. So what I have is I have a minus and a minus, so that's going to be a plus r squared cos t sine t, and here I have a minus r squared cos t sine t. So this and that cancel out, and I've got an integral of 0, which is, not too surprisingly, 0. Right? And so the circulation around that is 0. There is no net result, no net effect, essentially, of the vector field along the curve. It doesn't have any tendency to circulate. Anyway, special case of line integral of a vector function along a curve. This is the circulation. Enjoy.